My name is Martin Seagate. I convened the International Glaciological Society British branch meeting in Bristol last September 2014. Now, as many of you will know, John Nye spent his entire academic career at Bristol, and so while the meeting was going on, a few of us thought it'd be a good idea to contact John and see if he'd like to take part in the meeting. He responded very well and said actually he'd like to give us a talk. We think it's the first time that John has given a talk to any glaciologist for over 10 years. You're just about to see a recording of that talk, which is really a description of his academic career and how he's first started in glaciology. It will be of interest to all glaciologists, I'm sure, and is an amazing insight into the history of our subject.
Thank you, Martin, for that kind introduction. I'm a physicist and I study optics and waves. Some people think it odd that someone studying optics and waves should be interested in glaciers at all. The answer to that question will become apparent. But I realized recently that I was the sole witness of an event that happened 65 years ago, which was, it might be said, it was the beginning of modern theoretical glacier mechanics. I want to tell you about that, and it will also explain my own involvement in the subject. The pioneer had been the brilliant James Forbes, who in the 1840s had realized that glaciers flowed down their valleys like viscous liquids, so much treacle, they said. Of course, it was rather thick treacle, and the snag with this is that, well, we all know that ice is solid. If you fall down on it, it doesn't feel like treacle at all, even hard treacle. It hurts. So there's something wrong with that, but it was still current. The viscous theory was still current in the 1940s. I was at that time a postdoc at Cambridge, although the term postdoc hadn't been invented then. My supervisor was this man, Egon Oravan, a Hungarian. He came from Budapest and Berlin, where he'd been educated as a physicist and an engineer. He came from Germany, it was Hitler's Germany. He came from Germany as a refugee in the 30s. And he had become quite well known in his field because he was one of the three people who simultaneously had the same idea for explaining the weakness of crystals. It's called a dislocation. I ought to explain what that is. If you put a stress on a crystal, it either breaks or it deforms plastically. If it deforms plastically, it deforms by slip or glide. Whole planes of crystal planes slip over one another by 1 unit at a time, 1 atomic unit. The trouble is that if you note the forces between the atoms, if you calculate how strong the crystal would be, how much force it would take to make that happen, you get an answer that's hopelessly wrong. It's 1,000 times wrong. The crystal is 1,000 times weaker than you calculate. There's something very badly wrong with the theory. And the dislocation is the idea that was put forward to explain this gross discrepancy. To explain what a dislocation is, imagine a heavy carpet. You're trying to pull it across a room. Well, it's too heavy, you can't pull it. The crystal's very strong. You try to pull the carpet and it's too heavy, so what do? You make a ruck in it, and you work the ruck across the room until it's got to the far side, and then the carpet has moved, and you haven't had to pull the whole thing in one go. for that's what a dislocation is in a crystal. There are rocks in crystals. They're called dislocations. They're lines. Now this rather simple idea became quite fundamental in the development of, first of all, metal physics, and then metal physics, as it were, turned into material science, and the dislocation became a key feature of many of the explanations given in materials science, where the explanation depended on the material being imperfect. The dislocations and other defects were the explanation of many properties of materials. So in short, Oravan was very well known in his field. Now in the Cavendish laboratory at Cambridge in the Austin wing, at that time, it was just soon after the war, 1949, we were very crowded, and I shared a room with Oravan, he being my supervisor. I say shared a room, actually we practically shared a desk. He sat at his desk, pounding away on his typewriter. My desk was back to back with his. And he had quite a number of visitors. And I suppose some of them were quite eminent. So it was a great education for me to listen. I could hardly not listen to what they said. And I suppose I occasionally joined in when I was asked. Now, one of these visitors was Vaughan Lewis, a lecturer in geography. He was interested in the so-called pressure waves that form at the bottom of ice falls. I can show you a picture of such a one. This is the Vaughan Lewis ice fall, Juneau, Alaska, which is named after Vaughan Lewis, although I don't think he ever saw it. The ice fall itself is on your left, on the left of the slide. You're just seeing the very bottom of it. And the figure there pointing is me, pointing at one of the crests in the pressure waves that are formed at the foot. Can you see above my head the light and dark bands? They're called Forbes bands. The waves, the crests and troughs, change rather imperceptibly into these light and dark bands. It's a subtle change. And you find them at the bottom of many ice falls. Vaughan Lewis was above all an enthusiast. But he was absolutely nuts about cirque glaciers. Every summer he'd take parties of undergraduates to the Lake District, North Wales, and they'd take with them theodolites, plane tables, prismatic compasses, levels, staffs, measuring chains. If there's anything else you can take, they took it. And what they did was to make maps of these geomorphological features left there by the glaciers. In Norway, the cirque glaciers are still there in their cirques. So Vaughan Lewis took parties to Norway. He loved going to Norway. Now, if some of you learned about these things during your A-levels, if you learned about cirques, combes, there's hollows that you get, or hanging valleys, U-shaped valleys, all those things. If you learned about those at A-level, it was something to do, I suspect, with Vaughan Lewis's enthusiasms, because he taught generations of school teachers, of students, some of whom became school teachers, and they would have eventually influenced the syllabus. Well, I'm not an expert on schools, but I think it might be all a bit unbalanced. Lewis had this idea of what he called rotational slip. The glacier rotated and it scooped out its hollow. I protested that if the ice found itself in a hollow with a sloping surface, there was very little it could do except rotate. But Vaughan would have none of that. He said, no, it isn't like that. The ice is scooping out the hollow. That's how it happens. He wanted to know what was the friction force between the ice and the rock, so that he could calculate about the erosion. He didn't know how to do that, so he came to Oravan and asked him. Vaughan Lewis had made a little model. He had made a contraption out of Meccano and a spring balance to measure it. And Oravan rapidly told him how you did it theoretically. But the significance of their meeting is that in the course of this conversation, Oravan himself became interested in the whole problem of glacier flow. As I said before, the current view was that the glaciers flowed down their valleys like viscous liquids. Well, Oravan knew very well, as we all do, that ice is just not, it's a polycrystalline solid, not a liquid, and it's near its melting point, so it will undergo creep. The metallurgists have known about creep since 1910. But nobody had bothered to ask the metallurgists, nobody had bothered to ask Oravan. So in a characteristic way, Oravan started from first principles and suggested three very simple models. First up there on the left, you see a tall column of ice, slender column. And he asked, how tall can it be before it squeezes out at the bottom? He assumed that the ice behaved like what is called a perfectly plastic solid. That's to say, if you put a stress on it, first of all it deforms elastically, and then suddenly at a certain stress it goes, it yields. It's got a sharp yield point. So how high can that column be before the yield point is reached at the bottom? He assumed that the yield stress was about 1 bar, 1 atmosphere. Then the column can be 20 meters high. Bill Ward, at the meeting where these ideas were first presented, got up and said, but that's just about the depth that the deepest crevasses in alpine glaciers go to. Of course, a crevasse is not a tall, slender column. It's very far from it, but it just happens that the mathematics is the same. Well, a glacier is a good deal thicker than 20 meters. So at the top there, middle, you see a rectangular block of ice. That was Oravan's model, just simply resting on a slope. How thick can it be before it yields at the bottom, in the lowest layer? Well, if you take the same strength as before, the answer is 100 meters. That's about right for an alpine glacier. Of course, it depends on the slope too. But 100 meters is the right order of magnitude. Well, then you say, look at the bottom model there. That's Greenland. Greenland isn't on a slope, it's more like resting on a horizontal base. There you have, in the middle, look at the forces on the right-hand half. You've got hydrostatic pressure on the left, pushing it from left to right, and it's got to be resisted by something, otherwise the whole thing would take off with the speed of light. So it's resisted by the shear stress on the bottom, and the shear stress can't be bigger than 1 bar. So you work that out. You put in the width of Greenland, about 900 kilometers, and you work out that the thickness at the center would be about 3,000 meters. Well, 3,000 meters is just about right for the central part of Greenland. Well, these simple ideas turned out to be the beginning of modern theoretical glaciology. My own contribution was to elaborate on those models, taking account of the fact that the deformation would extend all the way through the ice. You might say that these models were what any competent physicist would have done. But the physicists weren't thinking about such things. Things they were interested in were quite different. Anyway, they didn't read about the theory of plasticity. And Orevan's contribution really was to bring physics into glacier mechanics. The next character in my story is Max Perutz. The Max Perutz who was given the Nobel Prize for working out the structure of hemoglobin. I'm sorry, that's such a terrible slide. I've got a better picture later. Those were the Crick and Watson days at the Cavendish. But for Perutz, he was also a refugee from Hitler, from Austria. He was interned at the beginning of the war. His real love was mountains, mountaineering. And he had seized every opportunity of going back to the Alps. He worked on the properties of ice during the war. It was that project for building an unsinkable aircraft carrier from an iceberg. And they got interested in the mechanical properties of ice that way. But now he planned his famous pipe experiment on the Jungfraujoch in Switzerland. John Glenn was working in the Cavendish at that time. He was Perutz's research student. John had a fridge in the basement of the Cavendish. It had a glass window in the door, and inside the fridge was a specimen of ice being compressed. It was undergoing creep. We didn't call it that then, but it was undergoing creep by the Glenn flow law. So there was Glenn working away in the basement, and whereas John Glenn was Max Perutz's research student, I had been Orevan's. It was thought that people like John Glenn and me shouldn't actually be working on glaciers without setting foot on one of them. Now, when you think that actually we can perfectly well do calculations about the ice caps of Mars, I've done them, without actually going to Mars. So that view is questionable. Nevertheless, John and I went out to Switzerland. Actually, we went to first of all to the Mer de Glace near Chamonix, where we were met by Max Perutz, who showed us how not to fall into crevasses and to avoid various other hazards on glaciers. And then we went off by ourselves and we visited as many glaciers as we could in Switzerland. We finished up at the pipe experiment. As I say, it was on the Jungfraujoch. They had built an igloo, that's an igloo you see there, to protect themselves. And there's the cable being lowered down the pipe. And I asked Max Perutz, how long is this inclinometer? Or maybe it was the heater. How long is this inclinometer that you've got down the hole? That long, he said. That's a rather better picture of him, I think. Maybe at the back of that igloo, you can just about see the junctions between the slabs. It was built in proper Eskimo fashion. And we helped to haul that heavy cable up to the research station, which was just up the hill from us. It was very heavy, I remember. Well, the main outcome of Max Perutz's experiment actually was being able to compare the Glen flow law with what actually happened. One of the things at that time was there was an idea, very current, very popular, of what they called extrusion flow. The idea was that ice under the great pressure at the bottom of these glaciers became more plastic, they said. It'd be squeezed out like toothpaste. It'd go faster at the bottom than it will at the top. Now that whole idea is deeply flawed mechanically, but Perutz's experiment really laid it to rest because it just didn't behave like that at all. Meanwhile, back in Cambridge, Vaughan Lewis was sitting in his office and there was a knock at his door. There stood a young man who said, "I've come from Alaska. I built my own house there out of wood, of course, and I've come to Cambridge. I brought my wife and my young son, by the way, because I want to be your research student." Well, I suppose Vaughan must have said, well, that's a little bit unusual, you know, to come out of the blue just like that. And after a while he must have asked him, "Well, what can you do?" "Well, what do you want me to do?" says McCall. "Well, what I really like is a tunnel. I'd like a tunnel through a cirque glacier all the way to the back of it so that I can see the contact between the ice and the rock. I want to see the erosion at the back." "You want a tunnel," says McCall. "I can make you a tunnel, and I can make it straight too." That's McCall's tunnel. There's John McCall sitting over there on the left looking down his theodolite, and inside the tunnel, they're too small for you to see, is a party of Cambridge undergraduate geography students armed with miners' picks. Every morning they go out there and they'd have a flashlight, because it's dark inside the tunnel, so they'd move the flashlight around until McCall signaled, "Yes, it's on my crosswires." That was the point where they started digging that day. So they hacked away until they got to the, as you see, back to the rock wall. The whole thing was a great success. It went slightly uphill so that the water would drain out. You see there's a drain down there. At that point, a lot of people came to see this tunnel. I thought actually, to be quite honest, that it was all rather dull at the back wall. There was simply a contact between, rather clean contact between the ice and the rock. I couldn't get much out of it, but still they thought Vaughan Lewis was thrilled with the whole thing. At that point enters another character, Bill Ward. Bill Ward is an engineer who knows all about tunnelling in the London clay for the London tubes. He knows about soil mechanics. He's also quite a mountaineer. So he says, "Look, there's a very spectacular glacier west of here, you should go and see it. It's called Thors Bread. Up on the top there, along the horizon, is the Thors Bread. That's the largest ice field in Europe. And glaciers come spilling down from it, quite a lot of glaciers come spilling down into valleys. The glacier on the left there is called Thors Bread, after the Norse god of lightning, and the one on the right is called Thors Bread, after the god of thunder. That, if you look at that heart-shaped nunatak in the middle, the right-hand side, which is the Thors Bread side, you see there's a cliff, and a certain amount of the Thors Bread ice, actually quite a small amount, but a certain amount comes to that cliff and comes thundering down in the form of great blocks of ice which hit the bottom with a thud. They break up, and the pieces can roll all the way down to the bottom of that avalanche fan. You see the avalanche fan to the right. There they come together, and you can see that you can just about on the right-hand side see the Thors bands developing. That's looking down the glacier where you can see the Thors bands. Then they're rather clearly seen there, and in the top middle you see there's a moraine, slightly lighter in colour, which is encroaching across the glacier. That's where our camp was. We had what we call the tunnel camp on that moraine. The bands are pretty clearly seen there, but if you're down actually on the glacier, you don't see them like that. If you look down when you're on the glacier, what you see is that the whole surface is made up of a lot of little holes, and down each hole, the bottom of each hole, there's some rock fragments, either one or many rock fragments or little pebble. It's called the cryoconite. But the effect of it is that if you look at it sideways, you don't see that it's dirty at all. It's only when you look down, partly downwards, as here, that you see that they're really dark. We'll come back to the cryoconite in a moment. Do you see, about a third way in from the left, you can see a bright patch. It's rectangular. Now that's man-made. That's not natural. I wanted to know whether these dirt bands went all the way through like that, or whether they're just superficial. So I got a party of the undergraduates to armed with mattocks to clear a patch. We call it the gardening team, and they cleared that patch, and the idea was come back after a year and see whether it had regenerated. Well, that happened to be the last year of these series of about 4 expeditions, so we didn't come back. So I don't know what the answer was, but I'm going to leave it with you to figure it out. What do you think? Did it regenerate after a year or not? And at the end of the lecture, I'll tell you what I think. This is just the layout. Here's Thors Bread on the left and Thors Bread coming in from the top. The avalanche fan is that triangular bit. The dotted lines are the crests of the waves, and it's about 2,000 feet drop from top to bottom there. So it's really quite a nice fall. They're down on the glacier. We're looking up, and can you see the circle, the black circle? There's an incline marking the line of our stakes. It goes from the middle to the left. 2 inclines again, showing the troughs. I was, at the very beginning of this whole series of expeditions, I was tramping over that area there with a Professor Hollingworth. Professor Hollingworth was a very eminent professor of geology. He was Professor of Geology at University College London. He was much senior to me, we walked around on that area, and I said to him, "Well, what do you think?" He said, "Well, I can see there's been a push from over there." I think I wanted to be a bit provocative, so I said, "Well, there must have been an equal push from over there, because otherwise it would have moved, it would have accelerated and moved off with the speed of light." He thought a bit about that. Then he grunted, and he said, "Yes, yes." So I said, "Well, look, we can easily test it by putting in a stake here and a stake there, measuring the distance between them, and coming back next year and seeing if they got closer together." "Yes," he said, "but hardly worth it, is it?" I treasure that response. We actually put in, I think it was 22 stakes and quite a few others on the side to check on the transverse movement. For over 100 years, many people have put in single markers to measure the speed of glaciers. But I think nobody had measured a longitudinal strain rate by putting in more than one at a time. It seems strange, but I don't think that had been done. In fact, as I said, we put in a line of 22 stakes and a few more to get the transverse strain rate. I ought perhaps to explain that after the first year, Volness became ill, and I made a scientific plan and became the scientific leader. Bill Ward became the man in charge, and it worked out very well. The stakes melted out quickly, and the holes had to be re-drilled. That's a typical stake. Actually, I think it's near one of the highest ones. You can see some people up there at the top. And can you see a tiny little dot on the stake? That's the point to which we measured. Now those stakes melted out very quickly, and they tilted, and they had to be replaced, rebored, tilted. So you had to measure their tilt, the direction in which they were tilted, as well as their distances from the other stakes. So it was quite a lot of work. But we had lots of, I mustn't call it manpower, we had lots of help. The amount of work wasn't a problem. I want to explain, you see, if the melting rate was absolutely prodigious. It was 6 or 7 meters a year, all crammed into 3 summer months. So that's really quite a rate of melting. So if you can't leave a stake for over a year, it just melts out. So you think, okay, well, we'll put a rock there. We'll put a rock with a number on it and come back and see if it measure to that. But if you do that, you put a rock down, it forms a little pedestal of ice. It sits on a little pedestal of ice because it's protecting the ice from melting. And eventually it slides off that pedestal, so it's moved from where it was. So that's no good as a marker. So what you do is this. You take a little pebble, about a centimetre perhaps, you cover it in red paint, you put it down on the ice, and then you cover it with a slab of rock, which is just the right size. If it's too small, it's like the cryoconite, it just melts its way in. If it's too big, it forms an ice table and slides. If it's just intermediate, it doesn't do either. That's what you want. So you come back the next year, you find your little slab of ice with rock, with the red paint on, with a number on. You lift it up. If there's a little red pebble underneath it, that's your mark, and that's okay. That's the way you keep a marker, or the way we kept markers going for a whole year. Well, the result of all these measurements was, quite simply, that there was no compression and extension connected with those waves. We did measure that it was extending and it was compressing, but it's nothing to do with the position of the waves. It was just the glacier coming down the ice fall and conforming with the bed, with the unevenness of the bed. So they weren't pressure waves at all. So what were they? That was the question. It just replaced that question with the other question. So what, if they're not pressure waves, what are they? The answer came from a quite unexpected direction. Early on I found that there was a spare folding Kodak camera, and I took photographs. I set it up on a rock near our tent, and I pointed it at the Audience Bay icefall, and I took pictures in the morning and in the evening. I didn't want to, you couldn't leave it out in the rain. You see, it rained all the time. And I didn't want to use my own camera because it needed that. So when I left the glacier after a few weeks, I gave strict instructions that there were to be pictures taken every morning and every evening, pointing the camera at Audience Bread. The result was 38 days worth of pictures, 2 a day. 76, isn't it? And with those pictures, they were enlarged. They were originally 2 1/4 by 3 1/4, 3 1/4 by 4 1/4. That was the usual roll film size. And they were all made into half-plate enlargements and put under a cine camera, which was operated by the chief technician in the physics department, and I pushed them in so far as I could in register, registering by the fixed rocks that were on either side of the icefall. The result was the time-lapse movie that I'm going to show you. But I want to make one thing very clear. That the chief result is not the time-lapse movie, which is not a very good one. The chief result came by putting the negatives of the film, one on top of one another, under a travelling microscope, and measuring the displacement between two times. You can follow marks, natural marks on the icefall, for about 5 days before they just turn into something else. So you've got a time slot there for measuring the velocity. And the main result was a 2-dimensional velocity distribution over the whole icefall. Now, before we see that, let's look at the time-lapse movie. there were no fixed rocks to fit the camera on. You see, time-lapse pictures of glacier, lots of them have been taken, but they all needed a fixed camera. You couldn't do that in these circumstances. Everything was moving. The rocks were forming rock tables, and they'd slide off their tables. Huge boulders formed enormous tables, then slid, and even smaller rocks down to, as I said, about this size, slid away, and it was a very bad place to have a camp actually, but never mind, that's where we had to camp. This is the velocity distribution as measured. It's the main curve there which is highlighted, and you see that the velocity has a peak. There are a lot of points. They're not all on that line. Now the ones that are off the line, that's not measurement error, that's simply that those points were not on the center line of the ice fall, so they're going at different velocities. What we're getting really is a two-dimensional picture of the velocity distribution over the ice fall. The main point is that the maximum velocity is very high. It's so high that a piece of ice would take of the order of 1 year to go right from the top right to the bottom. That is very fast. It's much faster than we ever dreamt that the ice could go. We were very unimaginative. Vaughan Lewis was very keen on that tunnel at the bottom of the ice fall. And what happened was that it flooded. The water went in, and although it had been drilled, tunneled in at a slight uphill angle, still it went on flooding, and eventually it had to be abandoned. And the reason was, of course, that the ice was moving so fast that the tunnel was rotating. It was rotating in the bad direction, and it got flooded all the time, so it had to be abandoned. That was a pity. But this very fast movement was significant from another point of view, because in fact it explained the waves that we were looking at. Now let me explain to you how that is. The model is as follows. Imagine a piece of ice that's approaching the top of the ice fall. Here it is. It's coming, the front of it gets into the ice fall, whoom, goes down in about a year. The back of it hasn't yet reached the top, so it's very stretched out, and all those crevasses there, stretched out, and then the back end of it reaches the top of the ice fall, and whoom, down it comes, and it compresses it all again at the bottom. That's a very simplified view, but it gives you the main idea. So ice that's in the ice fall gets very stretched out. That's why it's crevassed. Now there are two sorts of element like this. Think of it that way. There are elements which find themselves stretched out in the summer. They're the sort of unlucky ones, because there's lots of melting and they lose lots of ice, and a lot of dust gets blown in from the surrounding mountains. They get very dirty, and then all that dirt is trapped when it closes up at the bottom. And then the other elements are the ones that came there and were doing that in the winter. They were the kind of lucky ones, because in winter the whole area is just blanketed with snow. No dust coming from the surrounding mountains. Some of the snow gets into the crevasses, and when it closes up at the bottom, that snow gets trapped. But that's a dirty piece of ice. That's a clean piece of ice. It's the summer ice that gets dirty. So, in a word, the crests are the ice that was there in the winter and was protected from melting. The troughs are the ice that was there in the summer and was badly melted. The crests are the ones that didn't get dirt in them. Have I got that right? It's the summer ones that get dirt in, and they're the ones that melt, that the troughs have the dirt in, and the crests are comparatively clean. So in a nutshell, that's it. That's the theory. It can all be expressed in terms of convolutions. A convolution of the velocity distribution with the yearly pattern of ablation. But if you don't like convolutions, then my hand-waving explanation may be better for you. Well, with all this in mind, let's return briefly to that white patch on the glacier, the one the undergraduates cleared with their mattocks. Well, my picture's this. Here's the dirty bit, and it's compressed at the end of the summer, and all that dirt is more or less uniformly distributed in this column here. Then these are years on the bottom. After the second, this is the second year, first year, second year. Second year, there's been a bit of melting on top, and this dirt in this top bit has become concentrated at the top of the column. That's the dirt you see on the glacier. And then after 30 years, we're down there where the patch was. 30 years worth of dirt is accumulated at the top here. We've come and cleared it away with our mattocks, so it's now become cleaned. Then, this is 60 years. 60 years later, all the dirt in here has finally become deposited. That's the moraine at the very end of the glacier. So my idea would be that after 1 year, if we had come back, it would have looked much the same, just a little dirtier, but very little. I wonder if you reach the same conclusion. This ablation theory wasn't born on the glacier. It had to wait until I came home. One of the reasons was very simple, that the theodolite measured to a better than 1 second of arc, I think 1/10 of a second. So you can't work out the theodolite readings unless you have 7-figure logarithms. We didn't have 7-figure logarithms on the glacier because that's a shelf of books about that, like one of the ones behind me, about that wide. And you can't take those on a wet glacier. No calculators then. So that was all worked out later. At home I realized if I assumed that the seasonal pattern of melting and movement, if that repeated itself just the same year after year, that we had all the data that was necessary to calculate just exactly what would happen to any element of ice. And I laboriously plotted this out on a piece of graph paper. And there at the bottom of the glacier were these enormous waves. There they were on the graph paper. I couldn't see why they were there. Then I gradually figured it out. And that was the notion that I just explained to you. So it didn't come easy. The penny just didn't drop immediately. Well, looking back, were all those measurements on the glacier really necessary? Yes, I think they were, because without them we would never have convinced the traditionalists that their pressure waves weren't due to pressure at all. However, it was a complete surprise that just 76 amateur snaps contained more than enough information to solve the whole problem. That really was a surprise. This lecture has really been about crossing traditional subject boundaries. To answer a question about pressure waves by measuring the strain rate field of the flowing ice would seem quite natural to a physicist, but not evidently to a geologist. Again, perhaps that simple experiment on the cleared patch was not quite so simple, because it supplemented careful observation and reasoning by interfering with nature and doing an experiment on it. Then again, when Oravan was asked by Lewis about cirque glaciers, the ideas from metal physics that came naturally to him were totally unfamiliar to geomorphologists and to glaciologists. There was a time in glaciology 65 years ago when a little physics went a long way. There were very few of us then, not like now, but we had the field to ourselves, without competition. How lucky we were.